Thanks for joining me to discuss software-defined performance engineering. My name is Irfan Ahmad. I am the founder and CEO of Magnition, which is a startup focused on bringing fully autonomous storage and fully autonomous memory hierarchies to reality in cooperation with the entire storage industry and to serve as a key supplier towards that vision. So today I want to talk about what I call software-defined performance engineering. So performance engineering has become an increasingly exponential complexity problem. So I started off my career as a performance engineer working on microprocessors, and then worked for almost a decade at VMware in optimizing performance and creating autonomous performance systems. What I observed was over and over again working on storage systems that the multi-dimensional parameter space for any given storage software or hardware system has grown significantly. So the number of parameters that affect performance has increased. So here I just have a conceptual diagram of just looking at three different parameters in a modern storage system or a modern database or software system with a memory hierarchy has many more than three. But even if we just look at three, this conceptual diagram helps us understand that different applications or different workloads, and here each colored dot represents a single application. So for these three different parameters, as we vary them for different applications, the resulting performance, which is represented by the color, the darker, the brighter the color, the higher the performance, that there is huge variation. There's a manifold that develops. So in reality, today what's happening is that the performance engineering practices are constrained in many different dimensions, and we really have to, as an industry, change how we do this. So today we do design time or release time benchmarking based on a certain set of workloads that we are testing, that we understand from our customer interviews are important. So based on that testing of some limited number of parameters and some limited actual values of those parameters, that we are selecting the shipping configuration of those parameters in our storage system. So let's take an example of this, like cache block size is a static parameter that is settable on a typical storage array, and the changing of that parameter could have an order of magnitude difference for certain workloads. So how do you then set that parameter? Well, today we run benchmarks, and we do that at release time or at design time. Now, as the number of parameters increases over time, that becomes a very difficult exercise. And here I'm showing with the black dot the sort of least evil settings of these three parameters that is selected. In fact, that may not be the best setting for any single workload, but it's just sort of the least evil. So now this raises a question. How is it that we can go and improve the state of performance engineering and make it more software defined? So there's a couple of different dimensions of this, but let's first look at make sure that we agree on the impact of this. So the impact of this that we have observed at Magnition is that the static data infrastructure today, the sort of static performance engineering, the one-time performance engineering effort that is commonplace in all of the enterprise storage and operating systems today, that leads to thrashing and scan pollution and gross unfairness and interference. Because not only is it that the one-time performance engineering effort, the static one, results in picking some parameters settings that are the least evil, perhaps, but not really ideal for any condition. But now that we mixed workloads, and the mixing of the workload adds another dimension, dynamic dimension, that results even further in additional problems. So overall, this is leading to higher cost, over provisioning, under utilization, and overall lack of control because of these uncontrolled situations. So what's the path forward? So software-defined engineering, software-defined performance engineering, we have to start a little and zoom out a little bit and start at the highest level. So at the 10,000 foot level, we need to just think about the overall problem as two timescales and two domains. The first on the left is our actual performance engineering and product design process. And on the right is the runtime behavior. And here I give an example of a self-driving car, which has to make a significant number of decisions all by itself. And then once it's deployed in the field, a storage array should be doing the same. And within a certain set of parameters that are specified by models, it needs to go and adapt itself. So if we look at the engineering, the central engineering organization, the performance engineering and the design, the software design organization, and then look at the field deployed fleet of devices, we actually can draw a observe, orient, decide, act loop, an OODA loop between them. Not only does the organization, the software performance engineering organization, need to operate in an OODA loop, not only does the hopefully increasingly self-aware device software need to run in an OODA loop, but actually there's an OODA loop between the two. So we need new thinking for building instrumented, controllable, self-aware software and hardware. And as those fleets are deployed, we need to learn about the actual variances that we're seeing in the confronted workloads and the optimal scenarios of running those workloads and bring those back as part of this instrumentation, orientation, and decision acting loop. So as a result, software-defined performance engineering now has two prongs, has two domains in which we must practice it. So on the left is going to result in a lot of simulation, design time analysis, and is going to lead to a performance lab and performance engineering experience that starts to get closer and closer to how a civil engineer would build a bridge today using designs and simulations and load testing that's done in software, in simulation, so that we can explore the edges and build much better systems. On the other hand, the actual software that is being deployed by the software engineers in the devices itself needs to become software that can be aware of its conditions and improve them by changing parameters in safe manners, in a manner that is self-aware and takes into account cost-benefit analysis, among other things. So in both sides, both the runtime, self-awareness, autonomous device strategy, as well as in making our engineering processes more and more predictable and more simulation-driven and scenario-driven and so on, so that the resulting software is better. So in both directions, combined is what I call software-defined performance engineering as a practice, as a discipline. So in our experience and in our deployments with customers, here's what we're observing. We're observing that the best, highest end storage development and performance teams are moving to a simulation-based CAD-like software-defined software design cycle. What this is translating into is while the software is being developed, while new features are being developed, while new performance capabilities are being developed, rather than simply having a hypothesis and adding it to the code and shipping it, we are entering another stage in the design cycle. And this is exciting, and in the world, in our industry, is a first. And we're participating in many customer engagements that are at this stage, where long before a new version of a device or a brand new device is shipped, that the characterization of it is done in software, in simulation. And that is leading to much better designs and much fewer mistakes and optimizations that end up and algorithms that end up not performing in the field because the study of the problems and study of the algorithms was not done sufficiently. So this is very similar to how, as I mentioned before, a engineer in the civil engineering discipline would design a bridge today, or a mold maker would, by first designing a CAD model, and then from the CAD model, running a whole bunch of simulations to understand the behavior of the part and the wear and tear and how that particular part of that particular mold would actually behave in the field. And then the other end of this, to complete software-defined performance engineering, are actual autonomous storage systems that are collecting information about their own behavior, analyzing it, understanding the workloads, analyzing the behavior of the workloads, building co-models, and then doing what-if analyses in real time and adjusting and improving the performance of the system and adapting it to the workload. Now, contrast this software-defined performance engineering loop with what we talked about earlier, which is the traditional method today of running some benchmarks in a lab and picking some parameter settings that will have the least negative impact on production systems, or leaving it to professional services later on to try to tweak the systems, which again is very problematic and difficult because the information required to be able to do proper management of these systems is very hard to come by in today's devices. So if we are able to move as an industry towards software-defined performance engineering, and this is the core vision for Magnition and our experience on both sides of this, working in the industry, that a whole set of new performance optimizations that have not been possible before have been prototyped and designed, and papers have been written, and mathematical proofs have been written about them, but have not been feasible to deliver because we did not have a loop in which we could be sure that these optimizations which can improve certain workloads by orders of magnitude, but should only be applied in those cases that the actual deployed systems can make these decisions and do them safely. So that's the opportunity for software-defined performance engineering. Now, there's a broad set of use cases for this. I'm not going to be able to go through all of them, but really the point is to walk through some of them and build an industry consensus around this. So obviously there's monitoring. So software-defined performance engineering implies that the type of monitoring that we are able to do for the deployed systems in the field, the fleet of devices that we're building and optimizing and improving and adding new firmware, new versions, and so on, that we do this in a different way. And that really has to do with that instrumentation has to become much more structured, not just speeds and feeds, but models. The monitoring itself has to be modeled. And I always like to think about this from the point of view of a self-driving car. One of the key things in self-driving cars is that it's not just about speeds and feeds. It's about interpreting those and having models, because those models are what really will help improve the state of the system, because the models will capture the structure. Now, once we have these models, we can have auto-select policies and dynamic parameters so that the system itself is able to adapt. And then for the field deployed units, the fleet metrics that we get back are able to help us build better and better and better policies and algorithms, which can then be selected from or selected among in the field by the devices themselves. Software-defined performance engineering includes going all the way to having these types of models be used to not just make systems better, but also make systems that are more reliable in the quality of the services they can provide. And this includes the holy grail, perhaps, in this field, which is latency guarantees. So at this conference, I've given another talk where I go a little bit deeper into what the autonomous storage vision is and how latency guarantees can fit into that. So I encourage you to go and listen to that as well. Accurate tiering. Now, modern systems, performance engineering, one of the reasons it's become more complex is with multiple tiers in the memory hierarchy, starting from the L1 cache in the processor to the L2, the LLC, all the way to DRAM. Then between DRAM and NVMe, whether that's on the memory bus or on a storage bus, and on and on. So the ability to do performance engineering across that complicated and that deep of a hierarchy is no longer manually feasible. This is why software-defined performance engineering has to really take its place in our daily practice of performance engineering for storage systems. Now, I won't go through all of these, but suffice to say that the increasing complexity in our systems and the increasing velocity and the volatility of the workloads really requires a new vision for how performance engineering can be done. Now, our experience from this is that if software-defined performance engineering is brought to bear on new designs, that we have seen the ability to quantify the impact of changes of performance optimizations or new QoS features to be done via CAD-like simulations. And we are seeing each design decision now go through tens of thousands of design simulations. And that results in accurate decision-making for performance engineers and for software engineers implementing these features in the design stage and in the performance lab stage and in production. Of course, once we're able to do simulations of these models in the performance lab, performance engineering discipline all of a sudden can help with accurate capacity planning of these systems, as well as SKU development and BOM optimization, which now allows software performance engineers to play an even more important role in the overall product development. And of course, performance improvements and latency SLAs we already talked about. So this is a new discipline emerging around how to do performance engineering in the lab and in the field. So Magnition ourselves have been working in this area for some time, and we have the StorageLab product, which the experience from running with multiple customers, for which I've already been talking about, right? This is what we're doing with storage vendors, storage array makers, storage device makers, and so on. This is based on a patented miniature simulation modeling methodology that is brought to bear to run, as I mentioned earlier, tens of thousands of experiments per day in a CAD-like simulation environment, and then taking those and visualizing the results and making sense of them, and then using them as a decision support system as part of the development of devices. So this ultimately results in a very tight loop between developers and storage performance engineers, and developers and performance architects, because now the cycle between the planning and the coding and the building and testing and releasing and the CI/CD pipeline now starts to become a tight loop. And that loop includes integrated pipelines that can do complete design space exploration of the parameters in the system, optimizing the parameters of the system, including things like caches, things like write policies, things like read heads, and then hundreds of other parameters. And then that learning then feeds back into the planning process with product management and development. So this is a new impact that software-defined performance engineering is bringing to bear. So finally, we would love to collaborate with the industry to take this further, because the software-defined performance engineering discipline is a very broad discipline, and there's many different components, starting from data placement optimizations and parameter optimizations, all the way to the fleet management and so on. So I thank you very much for taking the time to listen to my talk, and welcome the opportunity to collaborate and bring this discipline to the world, and result in, which we believe will result in much better, more autonomous systems and customer satisfaction improvements. Thank you so much.